Hello and welcome to another geometry lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 8, Lesson 3 on trigonometry and the calculator. So what we're going to be doing today is we're going to be getting more used to our three basic trigonometric ratios, along with how we can use our calculator just a bit to work with trigonometry. So make sure to have your calculators handy, okay? You want to have your graphing calculator and you want to have it in what's known as degree mode. So make sure it thinks that you're working with angles in degrees. Otherwise you might get yourself into trouble. Anyway, let's do a little review on what we've seen so far with trigonometry. In a previous lesson, we saw how similar right triangles gave rise to the three fundamental trigonometric ratios. It is important to know the definitions of these three ratios. Now, before we even move on, right, let's get that mnemonic up on the board, right? SOHCAHTOA. The sine ratio, whoops, that was supposed to be a C and it didn't happen because I'm trying to talk and write at the same time. All right, the sine ratio is the opposite side divided by the hypotenuse. Cosine is adjacent divided by hypotenuse. Tangent is opposite divided by adjacent. Sometimes teachers will put in little fraction bars like this to help students remember that it's opposite divided by hypotenuse, adjacent divided by hypotenuse, opposite divided by adjacent, right? We've got to have that basic knowledge down because that is literally the way these ratios are defined for us. Let's take a look at exercise number 1. For the right triangle shown, answer the following questions. Letter A. State the value of each of the following ratios, leave in fraction form. Okay, so, for instance, if I want the sine of angle A, I look at angle A, I look at the leg that's opposite angle A, and that's equal to 1, right? I look at the hypotenuse, that's equal to 2, and so the sine of angle A is simply equal to 1/2, right? That is its ratio. On the other hand, the cosine of angle A, right, again, here's angle A. The leg adjacent to angle A is the square root of 3. The hypotenuse is equal to 2, so the cosine of angle A is equal to the square root of 3 divided by 2. And finally, the tangent of angle A is the side opposite angle A divided by the leg adjacent to angle A. So opposite of angle A, we have 1. Adjacent to angle A, we have the square root of 3. And so the tangent of angle A is 1 divided by the square root of 3. Some of your teachers might ask you to get rid of the radical in the denominator. That's not an absolute requirement for me, so I'm just going to leave it as 1 divided by the square root of 3. But you should obviously do whatever your teacher is asking you to do in terms of simplifying that fraction. Why don't you pause the video now and figure out what the values of sine C, cosine C, and tan C are. All right, so for the sine of angle C, right, I really focus on the angle. The leg opposite of C is the square root of 3. The hypotenuse remains 2. So the sine of angle C is root 3 over 2, right? For the cosine of angle C, the leg that's adjacent is equal to 1. Again, the hypotenuse is 2, so the cosine of angle C is 1/2. And finally, for the tangent of angle C, we've got the side opposite of angle C, which is root 3, the side adjacent, which is equal to 1. So the tangent of C is root 3 over 1, which could be simplified to the square root of 3, but I'm going to just leave it like that. All right, great. Let's review something else we saw in the last lesson. Let's take a look at letter B. What is the relationship between the sine and the cosine values of the complementary angles A and B? And that actually should say the complementary angles A and C. A and B are certainly not complementary to each other, but A and C are, right? In fact, for right now, at least in this course, we're not going to even talk about the sine, the cosine, or the tangent of 90-degree angles or angles larger than 90. We're just sticking with these two acute angles. So what is the relationship between the sine and the cosine of the complementary angles A and C? So don't worry about the tangent. Just look at these. Pause the video now and see if you can write something down. All right, well, it's pretty easy, right? The sine of A is equal to the cosine of C, and the cosine of A is equal to the sine of C. And I'm going to write those down right here, right? So the sine of A is equal to the cosine of C, and the sine of B and the sine of C is equal to the cosine of A. So they are just switched. All right. And again, that is always true of two angles whose measures add up to 90. Anytime two angles have measures that add up to 90, the sine of one will equal the cosine of the other, just like this. All right. So let's take a look at letter C. Using your calculator in degree mode, which of the following is the correct value of the measurement of angle A? Use a guess and check approach. We will see an easier way later. Okay, now let's go back up to these values, right? Don't worry about angle C. I'm just trying to figure out how big angle A is. I know the sine's 1/2, the cosine is √3/2, and the tangent is 1 divided by the square root of 3. The nicest of all of these is obviously sine of A equaling 1/2, right? So let's come back down to here. We know the sine of A is equal to 1/2. So let's now take our calculator out and let's ask it, what is the sine of 20? What is the sine of 30? What is the sine of 40? And what is the sine of 50, right? As we discussed in our last lesson, the calculator has these trigonometric ratio values stored in it for each angle, both acute angles and not acute angles. So all I have to do is bring my calculator up. Yet again, let me remind you that there should be something that says degree right here, or DEG right here if you're using the TI Inspire. If you're using, let's say, the TI 83 Plus or 84 Plus, that's going to be located in a different location. If you're using a any other type of calculator, like a Casio or a Hewlett-Packard or something like that, you'll have to kind of look into how to change that mode. But it's simple enough, right? I can hit my trig button, I can hit enter on my sine, and I can put in the sine of 20 and hit enter. And the sine of 20, I'm going to just maybe round this to 2 decimal places, 0.34. So that's not right. Let's do the sine of 30. And there's my winner, 0.5. Right? I don't even need to look at these. Okay, and I don't need to look at them because the sine of 30 degrees is 1/2. So angle A must measure 30 degrees. All right, that's got to be its measurement. Okay, so the calculator again, because of the similarity of right triangles that share acute angles, the calculator has all of these ratios stored within it. We're going to take advantage of that as we move ahead. Now, since the values of the trigonometric ratios only depend on the measure of a particular acute angle, your calculator has all the values of these ratios stored in it. Let's take a look at exercise number 2. Which of the following is closest to the length of MN in right triangle LMN shown below? Think about which trigonometric ratio makes the most sense given the angle and the one known side. Use your calculator to get and check, and that should say guess and check. I have all sorts of typos in this particular worksheet. My apologies, that should say guess and check. Now again, we're going to see ways in future lessons to do this quicker, but right now I only want to use the tools that are really available to us. Now, what we're trying to figure out is the best choice, not the exact choice, but the best choice for that length. Now, the one angle I know is my 42 degrees. That is opposite of 42. And that is adjacent to 42. So what I need to use is my tangent ratio, right? My tangent ratio is opposite over adjacent, right? So it's all about tangent, right? The tangent of L will be opposite over adjacent. So let's actually figure out, let's just kind of take our calculator out, and let's ask it what the tangent of 42 degrees is. That's simple enough. Okay, so let's do trig. We go over to tangent, and we ask it for the tangent of 42 degrees. That's a pretty nice value. That's 0.9004. Maybe I'll just stop it right there. Okay. So, right, now keep in mind the tangent of that should be equal to nm divided by 20, right? So the tangent of L should be nm divided by 20. So the question is, which one of those choices for nm will get us a ratio that is closest to 0.9004? Pause the video now and see if you can figure out which of these choices makes the most sense. All right, well, let's just kind of go through it, right? We can do 14 divided by 20, 16 divided by 20, 18 divided by 20, and 22 divided by 20. I'm pretty sure it's not going to be the last one because that's going to be greater than 1. But, right, if I do 14 divided by 20, well, of course, 14 divided by 20, I'm going to get 0.7. That doesn't look right. 16 divided by 20, and that's 0.8. 18 divided by 20. Oh, I think that's it. 0.9. Right? 0.9, 0.9, roughly equal. And so choice 3 makes the most sense, right? Now, LM or NM is not going to be exactly equal to 18, but it's the closest based on the information that we're given in the problem. All right. Let's do another one that's similar to this, and hopefully has no typos in it. You never know, though. Exercise number 3. In right triangle ABC, angle A is a right angle, and the measure of angle C equals 34 degrees. Which of the following measurements most closely match these conditions? Okay, so this one's a little bit more tricky than the last one. Let's take a look at what we know so far. We've got a right triangle. We know A is the right angle, and we know C measures 34 degrees. So let's just kind of like get that drawn out. Okay, so I've got my right triangle. A is a right angle. All right, C and B. C is 34 degrees, and I don't really care what B is for right now. Okay. Now, each one of these measurements will correspond to one particular ratio or another for angle C. But I think what makes sense is to right away just get some basic values for what the sine of 34 is, the cosine of 34, and the tangent of 34. So I'm going to write those down here. Sine of 34 degrees, cosine of 34 degrees, tangent of 34 degrees. What I'd like you to do right now is pause the video, use your calculator, and just figure out what each one of those is equal to the nearest hundredth. Okay, they're all going to be messy. Go ahead and do that. All right, let's do it. Here we go. Let me just clear this out a little bit. Oops, that's not what I want. Let's try that again. There it goes. Okay, so first, sine of 34. That is 0.56, let's say, rounded to the nearest hundredth. Let's now do cosine of 34, and that's going to be 0.83 to the nearest hundredth. And now let's get tangent of 34, and that's going to be 0.67 to the nearest hundredth. All right. I'll put that away for a second. All right, so we know these. One set of these values is going to correspond to one of these. All right, let's take a look at number 1, where we have AB equals 18, and we have BC is equal to 12. Okay, so, right, what would that allow me to do? Well, the 18 is opposite C, and the 12 is the hypotenuse. So that would be the sine ratio, right? This would be sine compared to angle C. So in this case, we'd have sine of c equals 18 divided by 12. And if I just do that real quickly on my calculator, 18 divided by 12, I need that as a decimal. That's 1.5. All right. Since the sine of 34 is not 1.5, that one is out. All right, that can't be the right choice. All right, simply the sine of c isn't 1.5. Okay, let me just erase these. All right, what's my next one? AB is equal to 14 and BC is equal to 25. That is, again, my sine ratio. Okay, so my ratio stayed the same in this case, right? I still have AB and BC. So in this case, that would be the sine of c equals 14 divided by 25. Let's again see what that's equal to. 14 divided by 25. And that's 0.56. And there's my winner, right? Sine of c, 14 divided by 25, 0.56. Sine of 34 is 0.56. That is my winner. Now, if I worked through the last two, which I'm not going to go through, but if I did work through these two, I'd find that none of them corresponded to these three values. None of them would be correct. None of them would give me the 0.83 or the 0.67. All right, let's keep working with our calculators in trigonometry. Now, in the old days, all right, instead of having a calculator, students had to read the trigonometric ratios from a table. All right, now, before we kind of even get into this problem, okay, in a certain sense, even though it's much easier to do trig on a calculator, the tables were kind of nice because you could really see the ratios, right? You know, you'd have an angle, like in this particular table, this isn't everything, right? But you'd have an angle like 25 degrees and you'd be able to see the sine ratio, the cosine ratio, and the tangent ratio. And having them kind of laid out like this gave you a sense for how those ratios kind of changed as the angle itself changed, right? Notice, like, as the angle gets bigger, your sine ratio gets bigger, but your cosine ratio is actually getting smaller. All right, and again, we won't get into that right now, but you'll look at that a little bit more in Algebra 2. Let's take a look at exercise number 4. A partial table for the trigonometric ratios is shown below. All ratios have been rounded to 4 decimal places. Answer the following questions based on the table. Letter A, without using your calculator, what must be the value of the cosine of 63 degrees? Explain. All right, so my claim is somehow, without using your calculator, you can figure out from this table what the cosine of 63 degrees is. See if you can figure out why that is. Pause the video now. Well, what should be true is that the cosine of 63 should be equal to the sine of the complement of 63. All right, so without using my calculator, I think I can do this. 90 minus 63 is equal to 27. All right, so the cosine of 63 degrees should be the sine of 27 degrees. All right, and that I have. That's right here. So the cosine of 63 degrees should be 0.4540. And by the way, that is the main reason why you're supposed to know that fact about the cosine of one angle being the sine of its complement. In the old days, these tables only went up to 45 degrees because you didn't need to go past 45, given that you could always use this kind of relationship. Let's take a look at letter B. Which angle in the table is closest to the measure of angle A shown in the right triangle below? Justify your answer using a trigonometric ratio. All right, well, how in the world am I going to use this table to figure out the measure of angle A? Well, if I look at this particular right triangle, right, and I hone in on angle A, it's always about the angle. The 50 is the leg that is opposite angle A, And the 77 is the length of the leg adjacent to angle A. So what I can say, right, is I can say that the tangent of angle A, which is opposite divided by adjacent, is equal to 50 divided by 77. And let me figure out what that's equal to. Let me just get rid of all this mess. 50 divided by 77 is 0.64935, etc. Okay, and now if I look at my table, right, and I go to my tangent column and I look for this particular value, 0.649, let's see, do we have it? Ah, there it is, 0.6494. That looks like A is 33 degrees. Or maybe I should say the measure of angle A is 33 degrees. All right, that's it, right? We can use that table to help us figure out what the measure of angle A is. But there's actually a quicker way to do it. Let's take a look at part C. Using your calculator, evaluate each of the following. Round to the nearest whole number. All right, so now you got to watch out because when you look at each one of these, there's your sine, your cosine, and your tangent. But notice that there's a little -1 that looks like an exponent on each one of those. Maybe let's go to the screen for a minute so people can really see that. Right, it says sine with a little -1 as an exponent, cosine with a little -1 as an exponent, and tangent with a little -1 as its exponent, right? Those are what are called the inverse sine, inverse cosine, and inverse tangent. So let's see how we get those on our calculator. We actually see them exactly in the same place as the trig. If I hit my trig button, okay, that's awesome. And I go to sine with the little -1, and now I put in 0.4384, and I hit enter. Rounded to the nearest whole number, that's 26, right? Now if I do the cosine one, whoops, that's not what I wanted. If I do the cosine one, and I go down to the cosine with the little -1 called the inverse cosine, and I put in 0.8290, hit enter, I'll get 34. And finally, if I hit trig and I go over to the inverse tangent and I put in 0.6009, right, I'll get 31. All right, let's take a look at letter D. What do you think the purpose of the inverse trigonometric functions are from letter C? Well, take a look at your table. Right? Now, if I look at the sine column, okay, maybe I have to go up a little bit more, and I find 0.4384, notice that corresponds to 26 degrees. If I go to the cosine column and I find 0.8290, it's got to be somewhere in here, there it is, 0.8290, and I go across, that corresponds to an angle of 34. And if I go to the tangent and I look at 0.60009 or 0.6009, right, that corresponds to an angle of 31 degrees. So each one of these is kind of going in the opposite direction. It's taking the ratios and it's giving us the angles that have those ratios. And that makes sense, right? If our calculator has this table sitting inside of it somewhere, right, then it can take an angle and give us the ratio, but it can also take the ratio and give us the angle. So what do you think the purpose of the inverse trigonometric functions are? They find the angle that has a particular trigonometric ratio. Trigonometric. It's a long word. trigonometric ratio. And that will make finding angles in right triangles whose side lengths are known exceptionally easy. Let's take a look at how that's done, right? The inverse trigonometric functions. Let's talk about these for a minute and then we'll see how to use them. The inverse sine, or sine with a little -1, x, the inverse cosine, the inverse tangent functions give an output that is the angle that has the sine, cosine, or tangent ratio that is the input to the function. All right, that seems weird. Let's see how it works in practice. Exercise number 5. Given right triangle CDE shown below, letter A, what trigonometric ratio will relate angle E to the given side lengths? Set up the ratio. All right, so in other words, here I've got angle E. All right, I know this side of 8 and I know this side of 11. What ratio can I write down based on that angle and these two sides? Pause the video now and see if you can figure that out. All right, here we go. Well, it's all about how these two sides relate to angle E. The 8 is the adjacent side, and the 11 is the hypotenuse. So of the three ratios, it's the cosine ratio that has the adjacent side and the hypotenuse in it. So I can say that the cosine of angle E is equal to 8 divided by 11. Okay, great. So I know what the cosine of E is equal to. It's equal to 8/11ths, right? Which is some ugly decimal, one or another, right? Now let's look at B. Use the inverse trigonometric function from part A to determine the measure of angle E to the nearest degree. This is cool because I can now say, since the cosine of E is equal to 8/11ths, I can say that the measure of angle E is equal to the inverse cosine of 8/11ths. Now you want to watch out. It's very easy early on for students to say, well, then the measure of angle E has to be equal to the cosine of 8/11ths. No, no, no. The cosine is 8/11ths. What I want to know is what angle has that ratio. But that's simple because now I can take my calculator out, hit trig, go down to the inverse cosine, type in 8 divided by 11, hit enter, and the measure of angle E, and a lot of times students will just say E equals, they won't say the measure of angle E, that's okay, is 43 degrees, measured to the nearest degree. All right, how easy is that? So simple, right, to figure out. And of course, it would make some of the problems that we did earlier in the lesson very easy, right? As long as we know two sides of any right triangle, we can use then the inverse trig functions to come up with either of the two acute angle measures by just simply doing the inverse sine, the inverse cosine, or the inverse tangent, and then putting the ratio in there. All right, let's summarize. And let me put my calculator away now. So today, we reviewed what the three trigonometric ratios were and how they relate angle sizes to the three sides of right triangles, all right? We also saw how to bring the calculator into that by doing some guess and check work, and also by using the inverse sine, the inverse cosine, and the inverse tangent to figure out the size of an angle, the degree measure of an angle, if we knew the particular sine, cosine, or tangent ratio. All right, and that's going to be one of the two main things that we do with trigonometry. We're going to really just use trig to do one of two things. Either find the size of an angle in a right triangle, or if we know the angle and one of the sides, to find one of the other sides. And we're going to concentrate on that a lot more in the next lesson. For now, I just want to thank you for joining me for another geometry lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.